reducing grain size and forming solid solutions, and cold working along with uh, the forming of precipitation. And we also have talked about the three stages of heat treatment, which includes is recovery, recrystallization, and green growth. And I hope you guys can understand all these concepts very, very clearly. And so you do not just have very good grades for this material science class, and also you know this basic and the fundamental knowledge. And so this is very, very important for you to get a good job and you can serve the country more effectively. Here are today's objectives for today's lecture. And first, we talk about ductile fracture and brittle fracture, and microscopically. And then we talk about the principles of fracture mechanics, and then we talk about the fracture toughness testing. Mechanical failure. The mechanical failure, and as mechanical engineering major the students, and so you need to know this mechanical failure. So there are several different kinds of mechanical failure. For this one, this is shape cyclic loading from the waves, and we know that in the ocean, um, uh, we have waves, cyclic periodically, and so as a result, the ships will experience the cyclic loading as the time goes, and so the shape that experienced the cyclic loading can break suddenly. So this is a catastrophe. This is kind of unexpected failure, which is catastrophe. So we need to do a lot of things to prevent the failure of ships under the cyclic loading from waves. And second one is computer chip cyclic thermal loading. And we know computers, and each of us has one or even more the personal computers and also other electronic devices. And we know that the computer chip and they experience the thermal loading. Thermal loading is kind of different from mechanical loading. Mechanical loading is that you apply the force periodically. That is called cyclic loading, mechanical loading. For thermal loading, it is also still loading, but in the form of thermal expansion or thermal shrinkage. And for example, for this chip, if you are working very, very hard, and so this is a chip, this is a computer is running, say suppose it runs every day, is at a very, very high temperature, and everything um, is expanding, right? So because we know all these items except the water, and expands at high temperature and shrinks at low temperature. And so this is one case scenario. Another case scenario is that when you turn it off, turn the computer off, and then this is the electronic these is small devices components in the computers and will experience the thermal shrinkage. So this is thermal this is shrinkage. This is expansion shrinkage, and this is cyclic loading. Uh, in response of thermal. And so this is called thermal cyclic loading. So this thermal cyclic loading can also um, result in catastrophic. This, this is a consequence. That means sometimes suddenly the chips the break unexpectedly. And so this is the second case scenario. And third case scenario is hip implant and cyclic loading from walking. And for some people, they who have this is hip implants and they still walking, right? We know when we walk. Um, so this is the hip experience the cyclic loading, and when you just land your leg and foot on the land, and there is one loading, and then you just take this is the your foot and leg off the ground. That is another loading in the opposite direction. So as a result, this is also um, result in the hip impacts implants also experience cyclic loading from walking. So these is three very important key scenarios that affect our lives um, substantially. So we just give these three very bad cases. So we want to do something to prevent this kind of this failure from happening. And then we talk about uh, mechanisms. And first we talk about fracture mechanisms. Right? So these are fracture mechanisms and the ductal fracture. And so what is a ductal fracture? As the name suggests, it includes this significant plastic deformation. Right? Plastic deformation means that if you apply too much load, so this specimen will not break immediately. On the contrary, this specimen will experience the plastic deformation at the very beginning. Then, as the time goes, and also as the loads grow, and so they have um, plastic flow, and then finally, and they break. So another category is brittle fracture. As the name suggests, brittle. Brittle, we can imagine that brittle fracture um, happens for brittle material. Brittle material means that when they have very high the loading conditions, um, so this specimen does not experience any or very little plastic deformation, and then immediately this specimen breaks. And so this brittle fracture is catastrophic. Okay, so catastrophic because there is no plastic deformation, and there, you do not have time to do anything to prevent this brittle fracture from this happening and from continuing. And so because if this brittle fracture occurs and this is a fracture, it fractures and continuously until the whole specimen the breaks. And this slide shows the comparison between ductal and versus the brittle fracture and classification, fracture behavior. And so this is a very ductal, and so this is moderately the ductal, and this is a brittle. And you can see very clearly for very ductile material. And so this is when this material breaks, and so this is the two ends are very sharp. And for moderately ductile material, you can see also see this kind of intersurface breakage, intersurface. Um, so brittle material, and so these two ends are very flat. That means there is no plastic deformation. And so here is I'll give you an example the pipe failure. So here is a pipe, and this is one piece, and ductile failure one piece, and it experiences large deformation. And for this brittle material, and it breaks into many pieces, and you can see all these many pieces, these pieces, and they experience very small deformation, which means that they break, okay, very quickly when the load exceeds some threshold value. So this is very important. So this is what we want to prevent. This is a case scenario we don't want to our specimen to happen. So moderately the ductal failure, and so this is show you several stages here. And so this is a failure stages necking, right? So necking, and I think if you are taking mechanics of solids lab and you are going to do the tensile testing. For tensile testing, I have been teaching mechanics of solids lab almost every year. And in this mechanic solids lab, we for the tensile testing, we have three materials. One is this is the steel. One is the aluminum alloy. The third one is cast iron. Aluminum alloy and steel, and these two guys are ductile material. But the cast iron is brittle material. And so for this is a ductile material. In our case, for the cast iron, for this steel and aluminum alloy, and so that you can see clearly that the specimen experiences necking when you apply the load. And then you can see void nucleation. You can have non-void, small voids here. And then as the load grows, and so this void voids come together, and finally void grows and coalescence, and then finally shear at the surface. This is shear. This is a slip surface, and usually this is 45 degree, and so it at this surface it breaks. And so this is a fracture, and usually after this fracture occurs, and you can see, and we have a cone. We have this is the cup. Okay, so this is a cup and a cone. So this kind of phenomena indicates that. So this is moderately the ductile failure. So you can see here, right, so this is a figure and shows particles serve as a void nucleation particles here. And so here is the fracture surface of this is a terracotta ware loaded in tension. So you can see this is a cup, right? This is cup, and another end is a cone, cup and a cone. And so this is almost 45 degree. So this surface forms an angle with axle with this is this axis as 45, almost 45 degree. Okay, theoretically it should be 45 degree, but because there are a lot of impurities in the material, and experimentally, so this is a degree is kind of off from 45 degree, but it is understandable. Any questions regarding this slide? No questions? We move on to the next slide. And then we just compare moderately ductile material and brittle material. So you will see this comparison. So this is aluminum. Actually, this is aluminum alloy. So here carbon cone fracture. So this end, two ends. And here is a brittle fracture. You can see the cast iron. So this is the two interfaces are very smooth. It shows that this is the surface almost does not experience any this plastic deformation. So this is the brittle material. Arrows indicate the point at which a fracture originated. From here, as the brittle fracture occurs, as I said, it will continue until this specimen fails. So brittle fracture surface. So you can see brittle fracture surface. So this is intergranular, and so as the name suggests, it is between the grains here. So we have the brittle fracture. This is 404, and stainless steel. This is metal. For this propylene, so this is a polymer, and so this is brittle fracture. Also, this is the breaking interface. So this transgranular, okay, transgranular. This is intergranular. Intergranular means that the cracks do not go into the grains, just along the grain boundary. Transgranular, as the name suggests, so this is a crack and goes into the grains and transverse. Right? So this is oxide, aluminum oxide. This is ceramic. You can see very clear the brittle fracture characteristic. And then we talk about ideal versus real material. So the stress, the strain behavior. Right? So here this epicenter is strain. The ordinate is the the stress. So this is a perfectly material, no flaws, but carefully produced. This is, for example, carefully produced glass fiber. So here's the tensile strength of this engineering material is far less than the tensile strength of the perfect materials because engineering materials usually have a lot of impurities. This is a typical ceramic. This is a typical ceramic, typically strengthened metal. The typical polymer. So Da Vinci, so this is 500 years ago, observed the longer the wear, the smaller the load for failure. Do you know why? Because the longer the wear, the more the, the higher possibility that it contains more impurities. More impurities will result in the reduction of stress. The reasons the flaws cause premature failure, larger samples contain longer flaws. Do you guys know Da Vinci? Okay, good. And then we talk about flaws um, are the stress concentrators. Suppose this is the specimen, and we have, and here is the floor, and this is crack, right? Central crack. So this is a wedge crack. So this is a crack, and so they are serving these tapes. They are serving as the stress concentrators. So stress concentrators means that at these locations, and we have relatively very high the stress when compared with other stress levels. You can see here. Okay, suppose so this is sigma 0. If we can imagine if we do not have any flaws, if we just have this nominal stress, and throughout this specimen, the stress level should be sigma 0. And however, because of the existence of these three tapes, the crack tapes, we will have stress concentration at these three tapes. So this local stress at these three tapes will be much higher than sigma 0. Right, so here, based on the Griffiths theory, for this is sigma m, and it equals 2 sigma 0, and so this is pt, the radius of curvature, and sigma 0 is applied force here, and sigma m is the stress as a crack tip. And so you can see very clearly that so this is the sigma m is much higher than sigma 0 because radius of curvature is usually very small. And you can see here. Alright, so this is the center crack, and at the two center crack tapes, we have so high stress level, which is much larger than this is a nominal stress sigma 0. And then we talk about engineering fracture design. Engineering fracture design, we have a rule. Okay, the rule is that avoid sharp corners, and also when I teach this mechatronics, no, I'm sorry, when I teach mechanics and solid mechanics, computer-aided engineering, or these manufacturing processes, and this is machine design, I always teach my students that we need to do our best to avoid sharp corners. Sharp corners are bad for the service life of the specimen of the components or system and you are designing. So avoid the sharp corners. You can see the sharp corners. We don't have sharp corner. We should not have sharp corners. You can see here. Okay, stress concentration factor Kt equals sigma maximum divided by sigma 0. So it's increasing sharp fillet radius. If the sharp fillet radius, so to the extreme, and sharp radius is equals 0. If this is equal 0, this is really theoretically a sharp angle. So it is very, very high. Okay, so you can see it's very so high. And if you have the failures here, and you can just reduce and the stress concentration factor KT. And then we talk about crack propagation. And cracks having sharp tips are propagate easier than crack having blunt tips. Right? So these are sharp tips, these are blunt tips. A plastic material deforms at the crack tip, which blunts the crack, right? Make the angle dull. But the brittle material and is a sharp angle, and as this crack grows, and it is go very, very fast. So here is the energy balance on the crack. Elastic strain energy, right? So energy stored in the material as it is elastically deformed. We know the strain energy. If you do something to the specimen, even if there is no cracks and it does not fracture, but still because you are doing the work to this specimen, the specimen's strain energy will be enhanced because the conservation of energy. We know that, right? So this energy is released when the crack propagates, and the creation of new surface requires energy. And as I told my students many times, all the physical systems, all the mechanical systems in the universe, they have the tendency to minimize the potential energy of the system because because the status with minimal energy is more stable. So this is understandable. Okay, so that means if you apply the load, um, if the load is too high and this specimen cannot withstand so much load, then the system will do something. And usually it breaks. If it breaks, and some amount of energy will be released, and then this system reaches another state of equilibrium in terms of energy. So this is what I always tell my students in several courses, such as manufacturing processes, machine design, computer-aided engineering, along with material science, and also other graduate courses, FEM 1 and 2, this plasticity, and also fracture mechanics, along with Abaqus modeling of composite materials. I always tell my students that all the systems in the universe tend to minimize their potential energy of the whole system. Why? Because the status with minimal energy is more stable. Then we talk about criteria for the crack propagation. We know if there is a crack, or at the very beginning, and under what condition the crack will have crack. So crack propagation, if crack tip stress sigma m exceeds a critical stress sigma c, is C critical. That means if this is inequality is satisfied, and there might be the crack propagation. So this is sigma c equals parentheses 2e gamma s tau a. Okay? A is 1/2 length of the internal crack, center crack, but for edge crack, so this is the whole crack length. Gamma s is a specific surface energy. Surface energy means that if you want to have this kind of surface, and how much energy you need to provide to the system. Young is the modulus of elasticity. And for ductile material, we can replace this gamma s, which is specific surface energy, and with the gamma s and plus gamma p. Gamma p is a plastic deformation energy, so be very, very careful about this. So I need to tell you this here in the material science class. I just talk about it a little bit. If you want to have deeper understanding of crack initiation criteria and crack propagation criteria, I would suggest that you take the fracture mechanics with you when you become a senior student, or when you enter this is the graduate program. And then we talk about the fracture. So the fracture, we can categorize this is a phenomena of the fracture into um, three the modes. One is the commonly seen mode, and it is called opening mode, open mode. Right? It is we call this opening. Opening just so this is the crack open. And second one is the shear mode two, and they call it shear or sliding. And sliding. So this one is for the mode one opening, and we can imagine the manufacturing processes when you use the tool to cut some material to get the final the products, and you will have this is mode one opening. And for this sliding, you can just imagine when you drive your car on the this is a kind of the soil. If the soil cannot provide you enough, uh, this is a traction, so your car will not move forward. As a result, and it's going rotating. You can see, so this is the sliding. We can just generally speaking, we can treat this one as a sliding. Also, this model two and the crack propagation. And so model three is a Therium. And so this Therium. This Therium out of this plane. Mode one is the most common crack propagation mode, and I want you to remember these three commonly seen modes, and which one is a commonly seen one mode, and it is opening. We have three different modes: mode one, mode two, mode three. And usually, because the complexity of the physical phenomena, are usually on the fracture we see the mixed modes of the fracture, which combines these three fundamental modes. Any questions regarding this slide? No question. We talk about very important the concept, the stress intensity factor, and is at the beginning, not the very beginning, at the several slides uh, before several slides, we talk about concept stress concentration factor. That is concentration factor is the results of having this is the cracks, flaws in the material as a result, and then in the neighborhood of these impurities or this is flaws, we will have the high stress level. That is called stress concentration factor. Now here is the stress intensity factor. You should know that stress intensity factor is exclusively related to fracture mechanics. Okay, and so it is a concept in the context of fracture mechanics. You understand? I want this is a new concept. I want you to underscore it and pay more attention to it to expand your knowledge database. And then we talk about the fracture toughness. And stress intensity factor Ki, so we focus on the mode 1 uh, opening mode. So this is K1, Ki. Specifies the stress intensity factor at the crack tip. Units is kind of weird, right? So megapascal square root meter. Meter is the length, megapascal is the stress. And usually we use this equation to calculate Ki. Ki equals lambda sigma m. Sigma m is a nominal load you applied. A is a crack length. And lambda is this is dimension is geometry correction factor. It depends on geometry, what kind of geometry your specimen has. So this is K, right? If this K is greater than Kc, critical value, which is the material parameter, and then this is a crack will happen, crack will propagate. So Kc equals y sigma, this is y sigma, okay? So this is y sigma, y multiplied by sigma square root of pi a. So here is fracture KIC is a critical value of stress intensity factor at which crack extension occurs. And so key point, and failure occurs when this n multiplied by ki is greater than kic. N is a safety factor. Usually, to be conservative, we don't want our system to fail. Usually, we use a safety factor that is greater than 1. Some people they are using 2 to 3. Uh, so this is to be conservative, we need to use the higher safety factor. Any questions regarding this slide? No, no, no. Then we talk about uh, geometry factor for initial crack shapes. So geometry factor, it depends on what kind of geometry your specimen has. For example, if we have load here, so this is central crack 2A, and so this is based on different ratio of A to this is W, and you will have different, this is lambda here. Lambda and Y, some people are using Y, and some people are using lambda, so this is the same. So this is another geometry, so this is edge crack, and based on the ratio of A and to this W, we have different lambda here. So this one for loading for edge crack, but this is a bending moment here, and we can have different geometry correction factor. And then we talk about yield strength and this fracture toughness data. You can see clearly that we have this is the yield strength and this is okay. Fracture toughness uh, range. So we have these metal, graphic, polymer, and composites. They have different fracture toughness. Fracture toughness means how easy it is. This is a KIC, okay? This is KIC here. And fractures stiffening and KIC uh, affecting this KIC. KIC diminishes with increasing street rate. KIC decreases with decreasing temperature. We don't know that the lower temperature, the KIC becomes lower. KIC decreases with increasing yield strength. And we know that toughness and this is ductility. Toughness is opposite to ductility, right? This toughness is kind of ductility, and it decreases with increasing yield strength. And KIC increases with ductility. They are talking about and kind of same thing. On key point, select a material with high KIC. And design against crack growth. Okay, crack growth. We use this equation. We compare this K and with this Kc, which is a material parameter. Largest, most highly stressed crack grow first. Okay, scenario 1. Okay, so max floor size dictates the design stress. We use this equation. Scenario 2, design stress dictates max and flow stress is a fracture. This area is fracture, this area is fracture. Material, this aircraft wing is an example. Material has KIC this one, two designs to consider. Design A, largest floor 9 mm, failure stress 112 megapascal. Design B, use same material, largest floor 4, and we want to calculate the failure stress. And how to do that? Using this equation. Key point, Y and KYC are the same for both designs because Y and KIC they are material parameter. Y is the geometry correction factor. Results, using this equation, you can get the sigma C for B case scenario. And then we talk about impact test. Also, in the mechanical engineering lab, you will do the impact testing here. So this is a hammer. We put a specimen here, and we use we just lift this hammer and then release it, and then this hammer is going to break. So this is a specimen, and then the hammer comes here. So this one is IZOD as I, letter I. Okay. So this one is CHARPY. And so this impact testing, and this is a severe testing case, make material more brittle and decrease toughness. This is a CHARPY, and so this is a CHARPY and this is IZOD. Impact testing here. So you can see these are two figures. Impact testing on different material, and they have different impact energy. Impact testing here. So here is the temperature and how this impact energy is related to the temperature. So design strategy, stay above the DBTT. DBTT means ductile to brittle transition temperature. So here is a pre-World War II, so the Titanic, and so here is World War II Liberty ships, because the ocean water was very, very cold. So summary, engineering materials not as strong as predicted by theory. Why? Because a lot of unpredicted, uncontrollable impurities, flaws. Flaws act as stress concentrators that cause failure at stress lower than the theoretical values. And sharp corners produce large stress concentration and premature. This is a failure. A failure type depends on the temperature and the stress level. For simple fracture, non-cyclic sigma and T is less than 0.4 melting temperature, failure stress decreases with increased maximum flow size, decreased operating temperature, increased rate of loading. For fatigue, cyclic stress cycles to failure fill decreases as this delta sigma, this is strength range increases. For creep, when temperature is higher than 0.4 multiplied by the melting temperature, time to rupture decreases as sigma or T increases. So this is the basic knowledge. I want you guys to know all these fundamentals. I hope you have a wonderful day, fruitful day, and I'll see you this Friday.